Hello everyone, my name is Tony George, a part of the Faculty of Science, and I'd like to introduce my project on the first steps on the synthesis of molybdenum dithiolene 2 complexes for the reduction of CO2. With increasing carbon emissions from fossil fuels, it started to negatively impact our environment in the form of global warming. One method that's interested scientists is the electrocatalytic reduction of CO2. This process can bring about a sustainable method of energy storage and conversion, as well as reduce the amount of carbon emissions in our air. This reaction leads to a variety of different products, and to the right of these products you can see the specific voltage required to drive the reaction forward, known as the standard equilibrium potential. Unfortunately, at this time there are little to no papers that have reached these ideal potentials. This is because the catalysts studied currently require a vast amount of overpotential in order to drive the reaction forward, meaning wasted energy, as well as low current density, meaning low conversion rates from our reactant to our product. One promising candidate for a catalyst that is also relatively cost efficient is molybdenum. The main reason why molybdenum was chosen, however, was because of its high current density in the reduction of CO2. In the Nature paper here, you can see that molybdenum disulfide, the red line, shows the highest performance for the reduction of CO2, performing even better than some noble metal catalysts such as copper and gold. The final objective of this project is to synthesize this molecule, which will serve as a more efficient catalyst for the reduction of CO2. There are a couple parts here that I'd like to highlight to why we're using it. The hydrophobic tail is used for the attraction of CO2 towards the catalyst. CO2 itself is a nonpolar molecule, therefore like attracts like. A nonpolar tail will attract our nonpolar CO2 towards the catalyst and therefore increase the formation of product. Our phenylene linker is used to attach our catalyst covalently to the carbon electrode. By having it covalently bonded to the carbon electrode, the rate of formation of our product will increase as the electron and proton transfer will be faster, making the process more efficient. However, there isn't enough time in the scope of this project to synthesize the entire molecule, therefore the objective of my project is to test the proof of concept for the first two parts of the project. We're combining techniques from organic chemistry, electrochemistry, and materials characterization. On the left here is the overall reaction scheme for the attachment of the hydrophobic tail onto a phenylene linker. Here we take 1,4-phenylene diamine, protect one of the amines using a protecting group, and then we react it with myristoyl chloride, forming our large hydrophobic tail. Through NMR analysis, we were able to confirm the successful synthesis of our desired product. To the right here, you can see the overall reaction scheme used to attach a phenylene linker onto a carbon electrode. Here we used a model compound, anthronylic acid, reduced it with sodium nitrite to form the diazonium salt, and then applied a voltage to blow off the dinitrogen species and directly bond it to the carbon surface. Through cyclic voltammetry, we were able to determine that we were able to functionalize our carbon surface, and through infrared spectroscopy, we were actually able to identify the C double bond O and the OH stretching bands of the carboxylic group on our carbon surface. Now, the next steps of this project are to deprotect our precursor molecule here, attach it to our carbon surface, and to synthesize the molybdenum dithiolene complexes to conduct our initial electrochem tests. I'd like to thank Dr. Coulter and Dr. Trevani for allowing me to work on this project, to the URA for this opportunity, and NSERC for the funding for this project. Thank you.